Okay, so good morning and let's get on with the subject matter of the course. Today what we are going to do is look into a couple of examples of signal processing algorithms to try and understand some of their computational characteristics and also look at a few architectures. What I mean by architectures is sort of pre-existing architectures and try and understand what kind of computational capabilities can be handled by those architectures and whether they are a suitable fit for the kind of applications that we are looking at. So a lot of what I'm going to do today is some sort of very quick back of the envelope calculations, so to say, right? And part of the reason for doing this is that I think it's good practice to understand how to do those things quickly, right? You don't need to have very accurate numbers, but you at least need to know what's sometimes called ballpark figures, right? Order of magnitude. Am I at least in the right, am I using roughly the right kind of architecture for solving a given problem, or is there absolutely no chance that my given architecture will be able to solve it? Or on the other hand, is it just overkill, right? I mean, is my compute requirement so low that I'm using something which is much more than what I need? So all of those are relevant and important questions when you are trying to come up with a useful mapping of a given algorithm to whatever architecture you have available to you. So we'll start basically by defining a few metrics. What I mean by metrics is some kind of numbers that are typically mentioned when we talk about how effective is this computation, or what kind of compute requirements are there, okay? And then we look at three different problems and very approximately try and estimate their computational requirements, okay? After which we will look at a few different architectures that exist and again try and estimate what are their computational capabilities, and sort of just to get an idea of what fits with what. All right, to start with a quick overview of metrics. It's just this one high level slide overview that I'm giving over here. There are a few different sets of numbers that you will often see mentioned in the context of how to qualify or measure the quality of a given architecture or an algorithm. One of the things that keeps coming up is the data transfer rate or the communication rate, right? And this is typically the number of bits that can be transferred over a wire or a bus per unit time, okay? So an example of this is, let's say that in fact we are using a microphone and we are trying to record samples of audio. Then ultimately that microphone is basically being connected by one wire to your A to D converter, and the A to D converter then has to basically pick up the data, convert it into a digital format, and then transmit it somehow. That transmission could either be over a serial bus or over some kind of a parallel 8-bit wide interface. All of those ultimately translate into number of bits that can be transferred per unit time, okay? The typical units for this are megabits per second, gigabits per second. You could have kilobits per second, but nowadays we are obviously, as far as this course is concerned, we are more interested in the high end of computation, right? The more compute intensive problems, right? So most of the time we'll be talking about megabits per second or gigabits per second. Having said that, there are applications, usually low power applications, where your data rates are low, and then we'll be talking about kilobits per second or possibly even just bits per second, right? The next thing after the raw data rate, how am I transferring information around, comes to operations, right? What kind of operations am I performing on the data that I have available to me? The most common in the realm of signal processing turns out to be something called the multiply accumulate operation, which is basically multiplying two numbers and adding it to something else, okay? So usually what happens is you have one register, you can think of it as a variable, which has some data that has already been accumulated over time. You have two other values, usually something like an input sample and a weight or a coefficient. You multiply those two together and add them to whatever was already present in the register. That operation is called a multiply accumulate, right? And is one of the most common operations in the domain of signal processing. So the number of multiply accumulates per second, typically M max, millions of multiply accumulates per second, or G max, gigamax, billions of multiply accumulates per second, are common metrics. Okay. Nowadays though, and in fact not just nowadays, it is historically, even before the advent of DSP, the most common metric in some ways was floating point operations. Okay. Now what exactly is a floating point number, what are the properties of floating point numbers, we'll be handling in a later class, right, because it is relevant to us. We need to understand a bit more detail about why we want to use floating point where possible, what are the advantages and drawbacks of it. But for the time being, one good way of thinking about it is floating point number is basically a real number. Okay, it can have a fractional portion, it can have an integer portion, it can have a very wide dynamic range. Okay, which is what basically sort of gives it a advantage over normal integers. So the number of floating point operations per second is usually referred to as flops. Okay, this value over here, FLOPS, all caps. When you see it with FLOPS all caps, it usually refers to floating point operations per second, right? There is also, unfortunately, one thing that you will see very often is just flop, FLOP, with possibly a small s at the end to indicate a plural, right? Where the FLOP over here just basically means floating point operation. So sometimes this can be a bit confusing. You are likely to see both being used interchangeably, and in fact I might also use them interchangeably, not interchangeably, but in the same sentence possibly. But usually it's clear from context whether we mean just the number of operations or the number of operations per second. Okay, so you need to sort of keep that in mind. You understand it clearly. Are you talking about just the raw number of operations or the number of operations per second? But the number of flops is essentially going to be our main metric for a lot of the computations that we are going to do later to find out whether or not what we are doing is computationally in what the requirements are. Okay, MIPS is an slightly older and nowadays very rarely used term. It basically stands for millions of instructions per second. There is also another acronym for MIPS or expansion for MIPS, which is basically it's the name of a type of processor. Okay, something the interlocked pipeline stages, but it doesn't really matter. Again, from context, it's usually very clear which one you are referring to. MIPS, if we talk about MIPS in this course, it is usually in the context of millions of instructions per second, but like I said, it's very rarely used nowadays, so we will not be using it much. And nowadays, flops of course is very well known. It's been around for decades. People understand exactly what you mean by floating point operations, and the number of floating point operations per second is a good measure. Not just, in fact, its use in the context of DSP and neural networks is relatively recent. It is typically used more in the context of really high performance computing, right? Supercomputers, where you are trying to measure the number of gigaflops or teraflops that a machine is capable of. Nowadays, with the advent of neural networks, people have been finding that full-blown floating point, 32-bit floating point or 64-bit floating point, is usually overkill for the kind of applications that we are dealing with. So there have been a number of different kinds of variants of architectures that have come up. You can still count the number of operations as the number of multiplications, number of additions, but it no longer really makes sense to talk of them as multiply accumulates or flops, right? Because in some cases they might be an application of some kind of a nonlinear function. In some cases it might be an approximate multiplication or an approximate addition. So rather than worrying about what exactly it is, people just call it ops per second, the number of operations, where the operation will be defined in the context of what you do. Okay, so all of these are going to be useful metrics. Primarily we'll be focusing on flops, but the others also could come up in certain contexts. Then of course comes the memory bandwidth, right? The number of bytes or words that are transferred per unit time. I am differentiating this slightly from the data transfer rate, which is usually just, for example, the output of an A to D converter, which is being transferred into a machine. In the case of memory bandwidth, it might not be from an external sensor. It might be that you are doing some computation, your data needs to be fetched from memory, acted upon, and then pushed back into memory. So what kind of memory bandwidth, how quickly do you need to be able to read and write that memory to process it. Okay. Once again, megabits per second, gigabits per second is possible, but usually megabytes per second, gigabytes per second are more common, because the assumption is that you are working with multi-bit data, and memory bandwidths are more often described in terms of megabytes per second than megabits per second. In some cases, especially for DRAM and all that, you will also see another term, MTPS, which is the number of transactions per second or number of transfers per second. Okay. The reason why this is different from megabytes per second is because then it starts depending on the width of the bus. DRAM especially, sometimes we now have very wide bandwidths, right? I could have, the minimum would be an 8-bit bus, but I could have a 32-bit bus or 64-bit bus, and nowadays high bandwidth memory has 1024-bit buses. Okay, so this is an extreme opposite of the sort of serial bus transfer that we are talking about, where we are saying that you actually have 1024-bit wide buses. They are used only for very short distance communication, just from one chip to another literally, but you can get fantastic bandwidth in that way. Okay, we'll look at that a little bit more moving forward.